Okay, in this video, we're going to talk about a new parameter, and that is the parameter that multiplies the input of a function. Generally, we talk about that as being b. So far, we actually have never used that kind of parameter. We have always added or subtracted the input, but we have never actually multiplied the input. When you multiply an input of a function, it causes the graph to change horizontally. We can tell it doesn't change vertically here because the high points are at the same height, the low points are at the same lows. This point right here at 0 is exactly the same. So what changed is the x values, the inputs. Now, when you multiply the inputs by 3, it actually is causing the graph to compress. All right, so it's maybe the opposite of what you would think. So let's think a little bit about why. Let's look at these two coordinates here. So f of -3 equals -4. To get g of -3, to get the g function to also have an output of -4. I apologize, it's because we're changing the inputs, not the outputs. So what do I have to do so that the output also is -4? I actually have to say, okay, so g of x equals f of 3x. So if f of -3 is what's right here, that must mean x was just -1. It's almost like we're solving the equation. We're working backwards. We're thinking, what did I plug in order to get out -4? So you can see here that I made the input actually divide by 3. I made it actually get smaller for the coordinates. Okay, and that's because let's finish off the statement here. Now we can say that g of -1 is equal to f of -3. So they have different inputs but the same output. And in those different inputs, f is always 3 times the value you plugged in for f is always 3 times the number you plugged in for g in order to get the same output. Another way you can think about it is that this f function, in order to get g, we're taking the f function and we're making it go 3 times faster. When things go faster, it makes the amount of time it takes shorter. So because we're speeding up the input, we're making everything happen in triple time, then when we actually go to graph it, it makes it smaller. So the compression happens, a horizontal compression, when b is greater than 1. So let's look for a second at what would happen if b was less than. Okay, as you might remember, if you make this thing you're multiplying in here, if you make the input negative, it causes a reflection over the y-axis. So in order to not have a reflection happen, I'm picking a b value that's less than 1, but still positive, so greater than 0. I can't actually make b, I could make b 1, but then nothing's going to happen. So that's why I'm stuck with strictly less than 1. And again, I want it to stay positive because if it were negative, it would cause it to reflect. So we're keeping it positive. So now look what happens here. So in this scenario, I have my parent function f of x. And now I'm saying g of x is equal to f of 1/3 of x. So if I want the value of g of x, I need to take 1/3 of x, and then I can get that value on the f of x function. So here I have g of -9 equals -4. How do I get that from f, right? I say, well, if I wanted to figure out what it was on the f function, it's 1/3 of this because g of x is f of 1/3 of x. So it's f of -3 that gives me -4. So since these are both -4, g of -9 equals f of -3. So to get g of -9, I look at 1/3. I look kind of backwards. I look at the smaller value, which is why g wound up getting bigger. Again, if you think about it here, to get g, I go at a much slower speed. I slow down. I'm only doing it 1/3 of the time, which is what caused a horizontal stretch. So just to summarize, if b is between 0 and 1, again, if b is negative, same things are going to happen, but it's going to reflect. But whenever b is positive, if it's between 0 and 1, you have a horizontal stretch. And if it would have been greater than 1, you would have had a horizontal